It's my pleasure to introduce Yusuf Aytar. Yusuf was until very recently a postdoc in Antonio Torralba's group at MIT, and he did really amazing work with Carl Fondrick. I think I got the name right, on audiovisual. Transfer learning between audio and vision, and now with text as well, I believe. And he's going to talk to us about this today. Thanks.
Looks like it sees it, but it's HDMI cable. All right, wonderful. That's clear. Thanks for everything. Thanks for inviting me. And today I will be mostly talking about deep cross-modal alignment and transfer, particularly focused on ambient sound understanding for this audience. But my work is generally, most recently, I'm a big fan of cross-modal learning and playing with different modalities and their interactions in between. And most of this work is a joint work with, while I was in MIT, with Carl Fondrick and Antonio Torralba. Currently, I moved to UK to DeepMind as a research scientist. So basically, well, just look at this sentence. The child tosses the stone into the lake. Like, as a human, we can actually picture a boy near a lake. We can even see the curves of the stone in the lake. I can personally hear the sound splashing. Like, well, even just from one sentence, we can perceive it in all these different multiple modalities. And it's just because, as humans, we can perceive concepts independent of the modality. Even though it comes in one modality, we instantly recognize it in other modalities. We can imagine in other modalities. And this basically this is something that we really want in machines to have. Why? The main reason is communication. Like cross-modal perception is very important for machines as well, because they're going to communicate with people, with us. And that's why they have to both see, hear, read, understand, and do all sorts of interactions, just like humans can do. And another inspiration is that the humans, we actually, when we're learning new things, we learn in the cross-modal environments. We see things, hear things. As the babies use this a lot while learning in this, in all these different modalities. So they just self-supervise themselves. They learn in an unsupervised form just by looking at both within modality and across modalities, the changes in time, changes in context. Like, machines should be able to do that as well, but we're not that good yet in this particular problem. And that's what I'm mostly looking at recently. So there are a couple of recent works in working on cross-modal aspects of vision and ambient sound. When I say sound, it's, again, not speech. Sound is not speech, kind of sound. So it's the natural sound, everything. It's simply the language of the nature that talks to us through different means. And there are a couple of works. One of them is Andrew Owen's work. Simply looking at from vision, can you predict some sounds in a constrained environment? The second one is from sound, predicting sound from vision to learn visual features. And the rest of the three today I'm going to talk about, so I'm not going to go in depth at the moment. So one of the challenges in sound is we don't have that much large-scale data sets in sound. Maybe recently there's audio set, but other than that, In vision, for instance, we have ImageNet, millions of images. We have places for scene categories. We have, again, probably at least 2 million in the first version, 10 million, I think, in the second version. And that applies to machine translation. That applies to a couple of other different domains. And one thing that we know about deep learning and all these recent things about AI is when you have large-scale data, then you can, with supervision, then you can learn pretty good models. But for sound, unfortunately, we don't have it. Maybe audio set can be an exception. I didn't really look deep into it, but that's definitely an interesting work towards that direction. So another issue about, well, working on vision and ambient sound together is there are lots of problems. Like, for instance, OK, now. OK. All right, so there's this clear background noise. Like simply the sound and, the sound and the image is not corresponding to each other at all. And then we have these other cases, like here. Like there are objects. There's a dog here in the background. You see the sound, but there is no dog in the vision. Just. Or you can actually have like pretty dark, not even that recognizable visual cues. Like there's all sorts of different noises. In addition to natural sound understanding problems, now you have all these cross-modal interactions creating more trouble for you. But at the same time, these are also good things, because this shows that there are certain things in sound which can complement vision, and certain things in vision which can complement sound. For instance, sound is 360 degrees. I cannot see the back of my head, but I can hear it. And that's pretty important for, like, for instance, you hear an ambulance much before than you see it. Or like another thing is in sound, you don't have actually any occlusion. Like in vision, I can't see the next door, but I can hear my baby crying next door. Like all these nice things in sound can complement vision pretty well, and the same applies to sound, vision complementing sound at the same time. So just by looking at these interactions, we decided to look at these learn sound representations from vision. So considering that in vision, we have pretty good models of understanding. So the main idea is there's lots of synchronous data with vision and sound, which is basically the videos available on the web. And we simply wanted to take the vision component, and we have pretty good visual models, like ImageNet models, places models, which can predict the objects, the scenes. In this case, given this image, we predict that there is a dog and beach in it. And then we take it as a supervision label, and then we train a sound network from this one. Basically, the vision module, which is already trained on large-scale data, it knows the environment pretty well, and it teaches our sound network. So the thing which we learn here is sound, the sound net part, and the sound is just coming with this natural synchronization between vision and audio. But of course, in order to do that, we have to collect a lot of data. And a lot of, when I mean a lot of, it's really like this is, well, while I was at MIT, this was a huge deal, like 26 terabytes of videos that you download from Flickr in our case. And the reason that we actually did it from Flickr is it's much less edited. You don't see that much. It's more natural, short clips of audios, as opposed to YouTube videos, which are relatively more edited if you randomly sample from that. And the overall architecture is simply this. We have these two different vision networks, which are previously trained. We don't do any training there. And then given any video, we take the frames. We separate the audio from that. And from the frames, we predict the object and scene distributions. And then we predict those two distributions with the sound net network. And the network is nothing too complicated. It's kind of an analogy of AlexNet. It's one of the initial convolutional neural nets architectures. It's just lots of 1D convolutions, decreasing the dimensionality as fast as possible. It's fully convolutional. In that sense, you can input a 5-second, 10-second, 100-second audio. It doesn't matter. It can generate a certain representation at the end. And the way that we train the model is basically with a KL distance. So we have the supervision coming from vision, and then we have predictions coming from the sound network, and our error is simply the distance between these two distributions. So I would like to give you a brief examples of it. So basically, the top three is the top three scene categories predicted from sound only. The vision is not used. And the bottom three is the top three object categories from the ImageNet. And I just blurred the video so that you can actually also do the prediction yourself. So here you can actually see that just from this baby noise, it can predict, say, diaper, bassinet, because that's what it constantly sees. When it sees children, it's either changing the diapers or like. This one is interesting. So just from the Happy Birthday song, which actually is a pretty long representation of sound, it can predict candles, it can predict restaurants, it can predict all these things around that might happen. It's not necessarily happening, but that might happen. And just from this sound, for me, it's really hard to see that it's a speedboat or that sort of a thing. But apparently, in the background, in that sound, it somehow gives that properties. And the same applies for many objects. Let me just stop it there and then move to the next. So, all right. So, given a large data set, we use vision to transfer sound and learn a sound network. But what does it actually learn? So let's look at different layers of this network to get more insight about it. The first layer is it's a relatively, well, when you look at it, you see some Gabor-like filters, you see some high-frequency, low-frequency filters, kind of a dictionary of things that it can use in the later layers. But when you look at the intermediary layers, now you started to see something more meaningful. So the way, what I'm showing you here is basically take one neuron in Conv5 and then run many test samples on that and find the maximally activating samples for that particular neuron. Here, oops, you can see, like, these are all different sounds that this neuron is mostly activating. And then another one here. Oops. Gosh, I'm not good at this. Okay. Another one. You see that they're still not at high level, but it starts to get high level. It's some certain type of noise. There's still background noise. And if you want to hear more, like in the website SoundNet MIT edu, you can find many of them. So when you go from Conv5 to Conv7, now things start to become more higher level. And again, the visualization is exactly the same. We take one neuron and find the samples which maximizes that. And now you start to see like an engine-like sound. Now the variation in the sound is a lot more increasing. Like for instance, let me go with the, oops. You see that different dogs and with different frequencies and entire mass. And it, oops, again, like another neuron focusing on bird sounds and noises. Sometimes it's really, really silent, but it can still understand with different amplitudes of the sound. And another one like sports chatter-like behavior. And you can find lots of different examples on the website about that. So now that we know that the network kind of learned something semantically reasonable entirely from a large set of videos, which we don't have any annotation at all. We just have good visual models of the world. So we wanted to test this one with different benchmarks. At the time, we picked up Decays. So this is Decays 2014. So at the time, there was only one, so we just said Decays. And basically, those are all the couple of entries at that time. And there's also this ensemble part, which is basically a combination of all of them. It was 78. And when we just take the sound features on Tool 5 and train an SVM on top of it, we see that there is a significant gap based on those results. Most recent features or the results may be slightly better than it. Actually, there are papers which are better than this one. Again, using vision, I'm going to talk about too. If you look at, for instance, another data set, this is a ESC data set, again, for environmental sounds. It's 50 categories with 4,000 sounds. And here you see more also convolutional baselines as well, like the person who introduced it, Pijak. He has a convolutional network trained on this system. And the performance that he gets with only this data set is around 64%. And if you just take the SoundNet features and apply it, you get a 10% boost. And the human performance, and untrained human performance on this data set is 81% on ESC50. And let's look at some more details about the network, the ablation studies. Of course, the KL loss is the main thing to train it, but we also tried L2, and the L2 doesn't perform that well on distributions. And we trained with ImageNet-only models, places-only models, both. Obviously, when you use both, it works better. And this part is interesting. Like we also take the SoundNet model, but we didn't train it on videos at all. We just take the architecture, the model itself, and train it on ESC50, this data set for 4,000 sound samples. And you can see that with 5-layer model, we have two different versions, 5-layer version and an 8-layer version. In a 5-layer version, you can actually see that it gets quite similar results to what Pijak got at the time, 64%. This is 65, slightly higher than that. When you go to 8 layers, it can no longer improve its performance. And the reason for that is basically it's overfitting. Like the data set is small. If you increase the depth of your network, it doesn't learn. It just overfits. And the main thing about deep learning is with more data, I mean, we know that when you get deeper, you learn better. But without data, you can't get deeper. And the way that we kind of achieve that is basically we train again a 5-layer network, now first initially trained with a SoundNet, like lots of videos, and then fine-tuned on ESC50. And you see that the 5-layer version, you don't see a much boost. From 65, it goes to 66. But when you increase the depth of the network, suddenly you see a much better, like maybe 6–8% difference as opposed to 5-layer version, because now you have enough data, you can train deeper networks. And I'm sure if we've actually trained much deeper networks from 8 to 10, 100, or 1,000 layers, just like they do in ResNets nowadays, we would have probably got much better results, but at the time, with the resources that we had at MIT, it was kind of limiting us, and this was the experiment that we did at the time. So we also wanted to see how these features look like. This is basically a visualization of, we collected a lot, I don't know how many, probably 2,000-ish samples here, and then we annotated in all these three modalities, the two modalities. And we show, what we show here is basically, there are these like urban, nature, work, home, all these different categories. And what we show here is using vision features, how TSNE embeddings look like, and using sound features, which is learned from SoundNet, how TSNE embeddings look like. You can see that vision is clearly grouping all these different semantic categories, and but sound is also somewhat getting there. It's not bad. And when you use them both, you actually get a slightly better performance in this particular case. So the second part of the talk is about basically learning an aligned representation across sound, vision, and text all together. So the previous one is just learning a single network. Now we actually want to learn a network which can understand image, sound, text, and kind of combines them all in a high-level representation. Just like, I mean, we humans naturally do that. No matter if I hear a car or if I see a car, similar neurons are firing in my mind, and I use it for decision-making and so on. But in order to do that, we need data. And the way that we collected data is, unfortunately, we don't have both sound, vision, text all together. But we have these different versions. Like we have, for instance, image captioning data sets. In that, we have lots of, like Coco has a lot of images with captions. And the visual genome is a lot larger. It's much simpler sentences. But again, you can generate around 800,000 images with captions, although there are repetitions in captions and some part of images as well. But it's still a decent data set for figuring out the relationship between text and vision. And then on the other side, we have this Flickr data set that we have sound and image data. So this particular work, we use spectrograms, but the previous work was using raw audio. So here, you can see that in this data set, we only have pairs of stuff, and only vision is common between the pairs. And basically, we want to train a network which kind of aligns in these higher layers. And how, well, basically, the behavior that we expect is, given a single neuron, we want it to fire on like a pool images or splashing sounds or text descriptions about the pool or jumping into the pool or that sort of relationships. And how are we going to do it? What's going to be the objective? So the first objective that we did is take the SoundNet idea, take the vision as a supervisory signal, and then predict those object distributions. Although the input also has vision, now the vision networks, basically this image subnetwork has to relearn itself to align itself with sound and text. And each of these networks has this modality-specific subparts, and then the aligned high-level representations, well, not aligned, but shared weights. And we hope that it's going to be aligned. But in this particular problem, we also have, we also have this other property, which is we have the pairs of data. And we can enforce pair similarity. We simply want, if a sound and image is actually a pair, we want their representation to be as close as possible on pool 5, FC6, some higher layers in the neural network. We want these two representations to be as close as possible if they're matching. If they're not matching, we want them to be as far away as possible. And we just implement it with a ranking loss, basically take the cosine similarity between sound and image and make a positive pair versus all the negative pairs. And there has to be a distance of margin, m. And that's how we learn, basically, or enforce a pairwise similarity. And we do it both sound vision and text and vision. And when we do that, this is basically training this complex system with 3 subnetworks, visual supervision, and also pairwise. Please.
Are you going to try to push apart the representation for a picture of one dog from the sound made by a different dog when you
it is possible. Well, technique. My objective is, obviously, I don't know what's inside the image exactly, but what I want to know is, given any video, I know that this sound corresponds to this video. And for the negative pairs, given any frames, I can randomly pick a sound, and quite probably it's not going to be a dog. So it's not there is no guarantees, but even with this noise, when you have large-scale data, it's highly probable that you're not going to actually get a dog. And that's what we count on. It's not a perfect data, but it's doing a pretty good job. And one way of evaluating how good or how aligned this representation is basically cross-model retrieval. Given an image, you want to retrieve sounds. Given one image, you want to retrieve or rank kind of sounds in your data set and look at what rank at the matching sound exactly is. This is generally people use this median rank. And lower is better. And we compared it with a couple of other baselines like CCA, normalized CCA versions. And also our model, what we see is when you simply use the model transfer, you get a lot better MEDAR score. And with ranking, it further improves because, obviously, you're trying to make pairs as close as possible. So it's doing a pretty good retrieval performance. But when you combine the model transfer and ranking together, you get a better performance. But of course, in these cases, we have image and sound pairs, image and text pairs, and they're all coming to us. But what is interesting is we have never seen text and sound pairs, but as a result, since the representation is aligned through vision, now we can actually, given a text, we can retrieve sounds related to that text, or given a sound, we can retrieve texts related to that sound. And in this case, the ranking loss actually is not the main one driving the performance. It's the model transfer, interestingly. But when you combine them together, you get a better performance again. These are a couple of visual examples of cross-model retrieval. Given an image, you can retrieve others. But what's, again, more interesting is I wanted to show you this hidden unit representations. Basically, what I expect is, given all these different modalities, no matter what the modality is, if the concept is the same, we want similar neurons to fire on that. And here is one selected neuron. And you can see that this neuron is focused on, if you give images, it focuses on underwater images and the things related to scuba diving, floating in the water, like watery, underwatery related text. And also, you can hear the top 3 sounds in the background right now. And we see, for instance, another neuron focusing on this kind of a behavior. Like it's firing on, mostly on images, and particularly with engine open. And also like the engine sound, and also text related to that one. So the interesting thing here is now, through this large-scale data, we actually learn a kind of a unified, high-level representation aligned across different modalities. And another example would go, top images, same neuron, but all these different samples. And of course, the babies. Like when you download videos on the web, this is probably the largest subset that you will find. The babies. Although Google find cats, we found babies. Anyway. So another interesting application of this one is basically, once you learn this aligned representation, now you can actually train a new category. We actually labeled 42 object categories in videos. In this case, we have both images, sounds, and text all together. We go for MTurk people and ask for doing that. And then we train a system. We fix the entire network other than the very last layer. And then we train a system with images. And then we tested that system with sounds of that category which has never been seen before by the sound network. Or the same, just test it with text samples, which is never seen of that samples. And what we see here is basically, although you don't see those samples, just because the high-level alignment between these different modalities, you can actually transfer this high-level learned behavior across different modalities. And this last piece of work, this is quite interesting, actually. I liked it a lot. It's by Relia and Andrew Zisserman at DeepMind. So in this particular work, they actually use no supervision at all. Like in most of my works, I use visual supervision as an simply for training everything. So in their case, they just use vision and sound to infer from each other, basically learn entirely from scratch. And this kind of like predicting the context to learn features actually exists in a variety of different domains. Like for instance, Word2Vec is just predicting, learning a text representation by predicting the local context. Same for skip thoughts vectors in text, or in vision, we have like jigsaw puzzles, like predicting the parts of the image or how to reshape the image to learn representation. Here, this one is a multimodal version of that. You're simply, the game is basically given an audio and a vision. You're actually trying to predict if these two are matching or not. And this data clearly exists on the web. Like you have lots of videos. And the way that they actually solve this problem is basically they have one visual convnet, which takes the images, the other convnet, convolutional network, which takes the audio in the form of a spectrogram, and then combines them together in a fully connected couple of layers. And actually, I'm going to show the architecture later. But the task that they are trying to solve is if these two sound and image matching or not matching. It's that simple, but this simple task actually learns a pretty interesting behavior, particularly both in vision, actually in sound as well. So let me first describe you what the architecture looks like. The architecture, this one is something quite similar to VGG network architecture, if you kind of know the vision models. It's lots of 3x3 convolutions, a couple of them, and then the max pooling, and then do it again and again and again up to a certain degree, and then combine them together with a couple of fully connected layers, and then you simply try to solve the task, which is either these two are matching with each other or not matching with each other. And how you generate data is obvious. You just take the matching videos, and then you randomly sample sounds and randomly sample frames, then you have the negative examples. And they, again, show they have similar neurons firing on certain concepts, like neurons like loans, like guitar, like bowling, and all these different visual and also sound-related concepts. And one thing that they can also do is look at which parts, the heat maps of those concepts, and actually overlay that with the actual images. Basically, now you know a neuron, you know that what sort of objects it fires on, and you can also highlight which parts is actually related to that. Since it's learned from vision and sound together, now you see that it's focusing on like certain parts of the guitar or the piano or whatever makes that sound in that image. It kind of focuses on those parts to figure out what that concept is. And they also show a similar audio version. And oops, come on. Like you can see some underwater category or some like clapping. Concert, windy, like probably crowds cheering. So it's, again, the same visualization. Take a single neuron, look at the maximally firing images, and then you get these activations. Not images, sorry. In this case, it's audio. But the previous example was the images. And the interesting part is they then take this and apply it to this ESC50 environmental sound recognition data set. And then what they actually see is this is the current state of the art on the data set, and the human performance is 71. And then they kind of see this 5% improvement on top of SoundNet results, which is, to me, it looks pretty good because you're now, I guess, 1% to the actual human performance, average human performance. So please. You can't.
Which one is the one you're talking about?
The very last one. So sorry about the size of it. So the one from the very last one is the most recent method, and the one before is the human performance. And the one before that is the SoundNet performance, the very first part that I talked about it. So this particular method, although it didn't use any visual supervision or anything high level, it actually learned pretty good features for doing environmental sound recognition. And particularly on this data set, of course, like it needs to be benchmarked in many others. And the same applies for the Decays. So our best results was 88, and the result of this particular paper is a 93, which is pretty good. And this is going to be a paper in this ICCV, like a couple of maybe not even a month, weeks from now. So, in conclusion, like this natural synchronization between vision and sound, and as well as all other different modalities, but particularly vision and sound, it can help us a lot on a variety of different problems. Like we can do cross-modal transfer, we can align different modalities, learn aligned representations that we can transfer across, or we can even use it as a very basic means of learning things, like self-supervision, basically. You hit something and you hear a sound, then it means something. Those are all correlated. And these correlations can actually guide us to learn much more richer features in all these different modalities: vision, sound, touch, art, depth, and everything. Thanks a lot.
Thanks a lot, Yusuf. This was great. Are there questions? Justin?
Thanks for a great talk. So could you maybe talk just a little bit more when you're combining? Thanks. Could you talk a bit more about how you represent text? So you take in images, you take in sound. I think a lot of people here are well familiar with that. How do you represent the text in these networks?
Yeah, in this particular work, basically we take a 16 words, maximum up to 16 words, and most of them are less than 16 words. For each word, we remove the stop words, we generate word-to-vec, and then we simply have this 300, which is word-to-vec dimension, by 16 matrix, and we run convolutions on top of it. So it's I think one of the Jan LeCun's or that group's paper from some time before.
Mark?
Yeah, hi, Mark Plumley from University of Surrey. So really nice talk and very nice work. I was wondering whether this could help the neuroscientists to understand how the brain develops the sort of concept cells. Is it the Halle Berry cells, for example, which you probably know.
Yeah.
What do you think you could comment on that? Could that help give insight to them in the work they're doing?
I mean, honestly, I don't have a neuroscience background or cognitive science background to actually talk about it in that depth. But I think it would be interesting to see how these behaviors are actually correlating with human understanding or perception as well. For instance, in vision, I think people did these works of looking at the visual features and looking at the brain what's happening in the brain when it sees, I think in primates, in certain visual stuff. And then they look at how these are correlated and how good it explains in vision. I think similar things can be done on SoundNet and this sound representations and perhaps even these multimodal representations. But I don't know if any work is actually being done on that particular problem.
I wanted to know could you talk a little bit more about how you can deal with the problem where things don't correspond because of music being overdubbed or sounds that aren't in the video and things like that? I didn't really pick up exactly on how you deal with that other than just getting rid of it in the data.
Honestly, we didn't really, I mean, the main thing about our approach is basically lots of data, a complex architecture, feed that in, and hope that works. That's the default deep learning understanding. But of course, while doing that, you want to do some form of controlled experiments as well. You want to make sure you want to have a control over your data. The first step is you don't have a control in the beginning because you know nothing. But once you know something, then you can actually see what's corresponding, what's not. And then you can downsize your data set for the ones which actually corresponds to each other. Did we do that? Nope, not yet. But that's definitely an important thing to do, because if your distributions in different spaces are different, then the chance that they transfer to each other or learn certain correlations, it's kind of, you decrease that performance. But without knowing anything about these different domains, you cannot actually learn a correspondence. First, you need to go in the wild and learn these cues, and then using those cues, now you can prune your data set and look at the ones which actually corresponds. The Relias paper, for instance, is given a sound and an audio. Now it can know if they are corresponding to each other or not. Like, given that, you can take millions of videos and downsize it a couple of millions, and now you have a pretty decent data set. But in order to do that, you need a lot of resources. Like, one of the main issues about this project, set of projects, is they are like, it needs a lot of storage, needs a lot of computation. You try all these different methods. The memory in the GPUs are becoming a problem when you want to do in multiple modalities, training all at the same time. So there are certain computational issues that needs to be taken care of. But once it's taken care of, with good handling of data, I believe that they will lead a lot more interesting representations in all these different domains.
Yes.
Thank you for your talk. I was trying to understand how well interpret your performance measure when you talked about the text to sound cross-modal prediction. You gave a median ranking performance, I think, of 135. I had no idea how to interpret that.
So generally, that analysis is mostly done in image captioning data sets. Like, given an image, you want to rank captions, and you generally have this 1,000 pairs of image and text. In this case, sound and text. And then within that within that data set, you pick a sound, and then you rank all 1,000 texts. And then you look at which is the exact match to this one. And then that's the rank of that. And what it simply says is 130, for instance. It says is you get a sound, and you rank the text, and the correct one is around 130. It's still not getting the best similar, but there is also a lot of confusion in the data set. Like, there's given one sound, many things matches. And actually, while we're generating this data set, we made this toy experiment with Carl. So I just sit behind, so he was sitting in front of the computer, I didn't see the computer, and he was running videos. I was trying to predict what sound actually, what sort of environment. It's very, very hard. Like, you have a rough idea about indoor, outdoor, but sound by nature, it's not that discriminative, but it's crucial at times. Like, on certain cases, it gives you a lot of information, but in most of the cases, you don't have that much information. And in this case, like in a 1,000 set, you may have a sound of silence or some noise, and then you're trying to retrieve a text using that noise. And even for humans, we didn't do human comparisons, but even for humans, I'm sure it's going to be a pretty hard job.
really enjoyed your talk. I couldn't help but reflect on some of the examples that you played, that many of them had a rhythmic or repetitive or oscillating event contained within the sound sample. You had fairly long sound samples. I just wondered if you could comment on that and speculate on the importance of rhythmic or patterned repetition in the scene in order to improve detection accuracy.
I mean, the nice thing about the convolutional networks is due to convolution, you can actually get a pretty good patterns which are across time or across any invariance that you want. And one thing about the, I'm not 100% sure if I get it correctly, but one thing that we did in the, for instance, benchmarking the sound net representation on these data sets is we take a sample, and then we take different subparts of the sample. And then for each subpart, we generated a score for that particular category, whatever that is. And then we run it through all these different windows, and then we take the mean of that to be more robust across time. Because obviously, in certain parts, you don't hear much, or like all these temporal relationships is important. And we just did a, let's say, ad hoc method to handle that. But the convolutions naturally in the convolutional networks are, while learning in all these different levels of abstractions, they're actually making use of this repetitive behavior across time.
Maybe one last question, and then we'll go to a coffee break.
So you mentioned the size of the network and the deep learning depends a lot on the size of the data set. Do you have any rules of thumb for like how much, because especially in a completely unsupervised setting, how much data per category you need in order to get like reasonable performance, or like how it scales with the size of the data set? And also, does the number of categories make a difference in how accurate you can be? Like if you have more categories that you in your taxonomy, does that confuse things, or is it kind of independent of that?
Okay, so most of the questions that you answer right now, the community of vision, and I guess in speech it's not going to be too much different, is we've simply experiment things on different, I mean, that's an unfortunate thing, but for vision, for instance, I would say when you have less than 100,000 images, don't expect much. When you have millions, then you start to see good performances. But it highly depends on what modality, what particular task you're looking at, and particularly in unsupervised learning, I think we're not even close to have good learnings in unsupervised learning. Like even in unsupervised learning, you can obviously have millions or billions of data if you would like to collect. But the trouble is the current methods are still not making use of that data good enough. Like we have autoencoders, we have all these different versions of cross-modality predictions, but still we're not there yet. Like we're still in the baby steps, actually not even close to babies, like in the very early ages. And that is a more of a model problem as opposed to a data problem in the unsupervised part. But when you look at the supervised part, it's mostly you collect your data, you identify your categories, and do empirical validation. And I would love to hear if there is other rules that based on some sound theory, but I didn't see that much, unfortunately.
All right, it's time to thank Yusuf again.
Thank you.